So what is superintelligence? Well, let's start with that. So it looks very animated.
It's very organic, huh?
It looks organic, but it's synthetic. It's completely synthetic. They started for like
Einstein was able, with the data that he had, to come up with new theories like E mc squared type beat. All right? Was that in his training data? Are we as humans capable of going beyond our training data? Welcome to Actually Intelligent. We're in Paris, the city of love, but increasingly the city of AI research. One person who did research here was Dr. Ben Zion. Today, I had a chance to interview him about his work on robotics farms and why it might be a missing piece to the puzzle in achieving actually intelligent systems. I'm Borvibe, a notorious vibe coder. I build apps with AI every day. If you do that as well, you know what these systems are already capable of, but you also know that they lack actual intelligence and sometimes run into very stupid mistakes. We're trying to figure out why and how we can build better systems. And today I'm with Dr. Matan Yah Ben Zion, who is a professor of artificial intelligence at the Donders Centre of Cognition and at the Radboud University in Nijmegen. Matan, great to have you here. Thank you for doing this.
Thank you for having me, Boris.
Can you tell us a little bit about your journey into the science of artificial intelligence?
Certainly. So my background is a bit diverse. In high school, I had a really good chemistry teacher, really good chemistry teacher. I took a lot of credits and extra credits in chemistry. But I also done a lot of extra credits in computer science. And when I graduated high school, I was at this intersection in life that I had to decide which path I'm going to go. And it felt that it will be either some CS path or some natural science path. And it felt to me that CS is a place where the kind of challenges that you're facing are challenges that people formed, like how to solve certain puzzles and so on. But the kind of challenges that you have in natural sciences were given to you by nature, by God, if you want, if you believe in it. It's like these are really open-ended questions that are out there, and felt a lot more intriguing to go in that path. And this is how I started my journey, which eventually brought me back to AI. I went to do a bachelor degree in chemistry, and it was in the Center for Physical Chemistry in Tel Aviv University, where they had really good researchers working on stochastic systems. So a stochastic system is a system that is characterized by some deterministic behavior. So you clearly know something will go from A to B. But there's also noise on top of it, and that noise is not trivial. So it will fluctuate on the way. And these stochastic systems sort of pervade all fields of life. It can be a stock in the stock market that has some fluctuations. Maybe it increases on the average, but it has some fluctuations. It can be a molecule that moves around. It can be a lion that roams the savannah. So on short time scales, it goes on a straight line, but on a days or weeks basis, it looks like it's just sort of meandering almost randomly. All these systems are, you will call stochastic systems, and will be analyzed mathematically in very similar tools. And the school that I was in was actually very good in these things, specifically for molecular, like the context was molecular. It was in chemistry department, but the tools are very physical and very mathematical in essence. And I think I really like the physics part. And then I end up doing a PhD in physics. Actually, first a master's and then a PhD in physics in New York University. This is how I was. We talked about New York earlier, and I spent some time in this wonderful city, which I really love and miss. And there I worked in the field that is known as soft matter physics. So soft matter, these are things that are not really solid, not really liquid, not gas. There's something in the middle. Formally speaking, you can say that they have high susceptibility, which means that if you push them in any direction, squeeze them, apply a magnetic field, you'll get a strong response. This is what it is by being soft, right? It's like a foam, right? You push it a little bit, it squeezes a lot. But you can also have a magnet that you apply a little magnetic field and it gets magnetized immediately. Or you can have, like your LCD screen that you apply a little bit of an electric field and the molecules rotate immediately and give you the nice display that we have now everywhere. So it's sort of a pretty broad spectrum of questions and challenges that span things from molecules to biological systems, and growingly so now also in sort of physics of AI. So because also in AI you have some input, and then you have an output, and the strength of the output could be of a really small push that you give into it. So you start now thinking about this in this high abstractization level, and it's sometimes the math is exactly the same. In my PhD, I was developing tools for self-assembly. Self-assembly means that you put a bunch of things together randomly, like a bunch of Lego bricks. Here, all my son's Legos, they're here. You throw them into a pile, and lo and behold, they self-assemble into a desired structure. This was totally planned to have these things all over the place. Yeah. Now, it's a very peculiar thing to have. I mean, to have all the building blocks just come together, just the right place, just the right orientation, and self-assemble. And while being peculiar, you see it everywhere, right? All of life is molecules that self-assembles, and they have some code that self-assembles them, and somehow it happens. So it's very natural. We're really bad at it. If you want to make a system that self-assembles to a pre-designed, structure, we're not really good at it, we as humans. And there are specific cases where we can do it well. And they're sometimes very limited. They're limited in size, so they work only in a very molecular level. And you and I are on the meter scale, so complicated structures can spontaneously self-assemble on a much larger scale. And being a PhD, you end up asking a very, very specific question. I was trying to make things that self-assemble on the micron scale. So this is roughly the size that cells are. So a cell or a bacteria are sometimes something like a few microns. And the question was, what do you need? What are the ingredients? Physical ingredients, mathematical ingredients, chemical ingredients that you need to pour into a tube that you let it shake, and then you'll open it, and then you'll have the structure that you want.
That's very interesting. I want to talk about the self-assembly for a bit, because this could be considered a form of intelligence, right? If you have a bunch of small, in your case, they will be very small, what you're talking about right now, particles, and you throw them together, they self-assemble in the structure that you desired, and you don't have to tweak it. If you would have like engineered on a human level scale some blocks with magnets in it in a smart way, that if you throw them together, they form a nice cube. Boom. Is that what we're talking about here?
It's not too far, yeah. And people have tried it. The way you just described. Smart people have tried it to make simple structures and failed miserably. I mean, it's embarrassing how much it failed, which tells you we're missing principles. We're missing principles in self-assembly.
Because you are right. If you look in nature, basically everything is self-assembled, right?
Yeah.
Nobody's out here putting the cells of a tree together. That just happens. So what? No,
Okay, so let's hold this thought as self-assembly. So when we're talking about self-assembly, I see you're trying to connect it with intelligence. It will connect very quickly. So this self-assembly level that we're describing is spatial. Its parts in space come together to make a structure, a physical structure. It has coordinates X, Y, Z, alpha, beta, gamma for the angles, and so on. So you started from random X, Y, Z of many particles, and then you sort of somehow converged spontaneously into this structure. A very similar process of call it self-assembly. I never thought about it as self-assembly, but this form of emergence happens also in intelligent systems, natural intelligent systems. So, for example, we know this better now, and especially now that I'm in a cognitive center. that, you know, our brains are not immediately hardwired to operate our body. So, for example, the neurons that drive your tibial, right, this hand, or the legs, sorry, the leg, that they, when you are born, they're not hard coded to control the leg. You get feedback. You have sensory feedback, and you crawl and you fall and you roll, and you have this feedback until the structure of, oh, if I activate this neuron, I move forward as much as I want.
Yeah,
Right?
it self-assembles.
So yeah,
Like,
so it's self-assembled, and the beauty in living systems is that these things are intertwined. They come together. They have to come together.
this is actually a random history teacher of mine gave me an example that might visualize it correctly, but I wanna run it by you. So speaking of the leg that you don't know how to move yet and it's self-assembled, he said like you could see your brain as a cup full of spaghetti, and the spaghetti will move in a certain pattern that then kind of that assembles in a certain pattern that kind of remembers if I do this and I do that. But it was like a super high level explanation. Does it make
Spaghetti
sense?
is pretty good. Yeah, you start with something disordered, spaghetti, stochastic even. Stochastic is usually in time, but you can also apply stochastic in structure. And yeah, and you need this feedback somehow to learn.
So one more question I had on my mind about the stochastic system, and then I'm going to bring it back to your timeline because I do want to finish it to where we are today. We weren't there yet. But so what is the difference? Is there even a difference between a stochastic system and what people would call a random system? Like you would just shake some.
So usually, when formally speaking, when you say stochastic, you imply there is some structure to the randomness. Random is it also a little bit field dependent. Many times when you say random, it means that it's completely random. So there are no correlations in space, like white noise. This is what you call random, but this is very formal. But you can have other forms of stochastic systems, of non of disordered systems. So there's no order in them, no clear order, but they're not just white noise. There's some other version of other type of noise. So you say it's colored noise. So it will look maybe random, but it will have some structure to it. So yeah, so these terms are sometimes used interchangeably. The word stochastic is sort of a very general version, and random is for a very, very specific, many times used for a very specific type of noise in the system. But this is formal, and sometimes it's field dependent. So you can say noisy, disordered.
Yeah, but the lion roaring about it's not completely random, of course. But it's because it has patterns. It will look for food, and you would, but it will be also quite noisy and random. So that is a good example for a stochastic system.
Yeah, exactly. So the examples with the line. So there is a nice paper. It's called "The Restaurant at the End of the Random Walk." It's from Klafter and others. He was one of my teachers in chemistry. He was one of the better contributions. He had some nice contributions to the field of stochastic processes in molecules. And yeah, and sort of what he implies there is that this picture that we already have for over a century, since, you know, Langevin and Einstein, and where the atomistic picture of materials was becoming to established. When it started to become established, it was realized that you have to think about these atoms because there's so many of them and they're constantly colliding and they're in constant commotion. You have to think about stochastically and sort of see what is the outcome that you observe as an average. The line case is a version of a stochastic process that is, yeah, it's not strictly random. They're not just going left and right, up and down randomly. Short time, you'll have some correlation. It's most likely to go straight. On a longer times, it might be, you know, confined to different regions where there are more zebras or so on. And if you look on a even longer time, then it would sort of smear out. There was a nice paper published, I think, in 2000 about where they tried to first measure motion of people. Now it's much easier because we are all now connected to this, and everyone knows everything about us. But they had a clever way of doing it by writing. They took $1 bills and they wrote on them, "If you see this, please log on to this website," and just so we can know where you are. And then they connected the steps that people did. And you see that there is unlike the lines, it's actually the other way around. There's a lot of small motion in short distances. So you go from Place d'Italie to Moulin Rouge. I don't know where you're going there. So it's small steps. And then the other characteristic was very big leaps of flights. And the first thing you see is basically the flight network, the aviation network, the global aviation network.
That's very interesting. I'm gonna try to find this paper later and then link it down in the notes so people can check it out. But Matan, we need to stick to your path, because you left me in New York, and you were in New York, out there, and you were loving the city, and you were learning a lot.
Yes,
on the PhD.
No,
So
we're going. We're going in this stochastic trip straight back to New York. So the paper is called "Where is George?" because he's on the bill. And you can look it up. It's a nice work. I really liked it. And it really captures this idea of stochastic processes of different colors. There it's called Levi flights. So you're making small steps, and every now and then you just make a huge leap. And then it was realized that in some circumstances, this is an excellent search algorithm if you're looking for, again, the restaurant at the end of the random walk. So during my PhD, I was looking into self-assembly. I would design this structure. It's called chiral tetrahedra. You put like billions of particles in a tube. They're micron in size, so you can put many of them. You wait a little bit, and then you get the structure that you design, and we design two left-hand and right-handed structures. That is very special. I usually have these things mostly in biological systems, and making them synthetically was kind of interesting. But I was very frustrated with it.
Why was that?
Because it was I wanted to make them bigger. I wanted to make them millimeter scale, meter scale, and the math sort of doesn't really exist for that. There are no principles because the principles that we use were thermodynamics. So how two molecules attract, and on average, what you'll get. I mean, they'll form a crystal, or they form a smaller molecule, or something intermediate. And thermodynamics gives you really strong tools to design these things, but it assumes that you have thermal motion, so things are just moving thermally. And this thermal motion is characterized by actual random motion, so it's Gaussian motion. Now that we're experts in stochastic processes, but once you're on a millimeter scale, you don't have that anymore. So an atom diffuses its size within like I don't know, a nanosecond, I think. It's like a single atom. It will just by thermal motion. Thermal motion means that it's being collided by other things. We will take a nanosecond. A micron particle, so it's roughly the cell size, moves its own size in a second. And a millimeter particle, just by thermal motion, by being collided with other things, I'm talking about room temperature, it will take it 25 years. So it's not reasonable to expect something that large to self-assemble just by thermal motion. We need something else. And this is how I started working on things that are active. So they're not just, they don't wait for things to push them around. They're self-propelled. Okay, so this already starts to lead you in a direction of, rhythm systems, and then robotics. Yeah, exactly. So I first developed these micro swimmers that are self-propelled. You shine them with light, and they start swimming. And they look like bacteria or something. When you look at it by like untrained eye, it's like, is this alive? It's sort of the first question. And it looks like it's alive exactly for this reason. It has this short time correlation, like you said with the lines. They sort of go straight, but they're not really just going straight. They also sort of meander a little bit and so on. So it looks very animated.
It's very organic, huh?
It looks organic, but it's synthetic. It's completely synthetic. They started for like oil tubes. This is where my chemistry background was sort of helpful, because I sort of had a picture of how to put these things together. They start from tubes in like oil tubes in the lab. It was just vials. It was completely synthetic. And then they started doing things together, which was the really interesting things, right? They started working together to do stuff. But the thing is that, like, formally, like, they were not designed to do anything together. It's more of the way we understand it now, it's more of a phase transition. It's like, a bunch of molecules will all arrange just in the right lattice, all pointing in the right direction to make ice once you go below a temperature. So in the same way that you have this phase transition, this emergent behavior of the collective from their interactions and their interaction with the environment, this is how we understand these microswimmers or this small swarm to do something together. It's like they essentially have a phase transition where they want to come together, and if there's something in the they want to come there, and if there's something in the way, they arrange it together. So it's like a swarm that puts together other particles, and if there's just scattered particles around, it can clean them and put them together in a single place. And you get it for free. You just get them from, like, nothing was computed. The individual was not intelligent. There was for free. So what happens in this experiment is we put, and this is sort of one of the fun things that happen when you're doing experiments. My attempt, from a synthetic point of view, I was attempting to get the purest form of microswimmers possible, so 100% them. But it ended up being, I don't know, 70 or 80 or 90%. I had some different batches. Some of them were pretty clean. Some of them were only 80% clean. And I sort of try to see what they do. I turn on the light, they start swimming, and I was just intrigued. Let's give them the opportunity to express themselves collectively. And I remember that first experiment that I've done with the 80% purity, or maybe less than that, I thought I burned the sample. It looked like black. It was not clear what was going on, but I still recorded. And for all these experimentalists out there that are listening, I saved it. And then I went back to that experiment, and I realized, actually, I have a very interesting experiment here, because I have microswimmers, or a swarm, that can operate on their environment, on these passive particles that are not swimmers. And once I looked carefully into this, because it's just microscopy, so it's not always clear what you're looking at, but once I look more carefully into it, I saw that what happens is that what you started off with a random distribution of the particles, so they're just, microswimmer or passive particle just randomly arranged, turned out to have all the passive particles concentrated and the microswimmers left. So, and once you look at the video, you see that the microswimmers there's some internal motion, and then you see microswimmers sort of pushing passive particles into this pile, and then they leave.
That's
Which
great.
was like,
But how does that happen? Because how did you design those micro swimmers, and what do you think is the reason for this happening?
so the way we understand this now is, this sort of was an observation. This is what I mean by for free. We didn't design them to do it. And the way we understand this now, and there might be even a better explanation, but our understanding sort of captures something quantitatively there, which was kind of nice, and is the following. So there are a few things you have to put together, a few ingredients you have to put together to understand this. One is that if you have just microswimmers,
Yes.
at a high enough concentration, they'll accumulate themselves. Because if they're very dilute, they'll just fly everywhere. But if they're very dense, say above 50% of density,
And
they'll
you make sure they are, so you confine them in a space where there's a 50% density.
I measure the initial. So the experiment is run as follows. You have some initial concentration. You start the experiment. You let them start running. They don't run it before you turn on the light. And then you see what happens. Okay, so if there's just one, and when we just started these experiments, we had just one, so it will just leave, right? It will fly off.
Yes.
So if you have 10, they'll sort of go past one another and fly off. If you have 100, what happens is that they start colliding, and then they slow down. And now you have a nucleus for others to collide and slow down. So you have this positive feedback, and they start accumulating, which is, by the way, a very important swarm behavior, this aggregation. It's like, how do you get a bunch of robots to come together in the same place? And here they do it just by collision. They just slow down whenever they collide.
I once, in a little app that I made, was playing with the Boyd's algorithm, right?
Uh-huh.
But there I set the rules for this types of behavior. But you're saying these did not have any rules.
But they were, I mean, they had rules.
What were the rules of these swimmers then?
Given by God. I mean, there are physical interactions.
That's your
I
passion with
can
nature.
tell you what are the rules that we understand, that we designed them to have. I mean, they can't overlap. The Boyd's model, I don't think they even have a volume, right? Boyd's model is the Reynolds paper from 1986 or 85. Yeah, so it's a really cool paper. Do you see the original paper? So what he does there, he says if we program these birds or fish models to align together, and we want to do computer graphics, computer animation, we don't need to make each and every item of the herd orchestrated specifically. We just give them rules, make a few of them, and then you have, videos like The Lion King and Batman, because you have this computer graphics that just tells them, oh, there's a flock of them or there's a herd of them. You get it sort of for free. You don't need to tell each and every one of them how they're going to move.
Yeah.
And, this is a very famous paper in the field, but turns out that there was an even paper that preceded that paper from the 70s, from the Japanese scientific fisheries, where they looked at fish, how they school, and they wrote effectively the same update rules for these alignments. The alignments were to give you schooling. So it turns out that and this is why it's like physical principles, like they span a lot of fields, right? And they're useful for fish and for computer graphics and so on. In a physical system, they collide, they slow down, right? In the Boyd, you can program this, you can hard code it in the Boyd's.
That's what I did.
But here you get it just from their natural interactions.
All right, I see.
And this natural interaction, this natural computation will come in later in our path. Keep it in mind. In my course, I'm teaching a course I'm studying next week again. It's called multi-agent systems. One of the exercises is exactly that. Show that you can program this Boyd's to flock. And they have a nice Python, Jupyter notebook. They can follow.
Super cool. I had to think about it earlier in the conversation as well, when you talked about this emergence of something that looks very organic, and that happens with the Boyd's algorithm as well. But let's go back into your journey. So you're now already quite close to where I met you. Is already dealing with these. So you have these micro swimmers, and you're discovering this that the non-active particles are pushed there, and we were kind of halfway in you explaining that. So let's pick up where we left.
Yes. So they aggregate once they're dense.
Yeah.
Okay. Now the other ingredient is the following: if you put particles, you can see it in your room even. If you put just random things all over the room, and maybe if you turn the camera, we'll see it. It will look very cluttered. Just visually, it looks cluttered. But once you just pile them together closely, despite occupying the same area, I mean, they have the same footprint, not even stacking them on top of each other, just closely, it looks a lot less cluttered. And this clutterness that we pick up by eye, it can also be described mathematically, because once two things are apart from one another, they effectively occupy more room than when they're touching each other, because if you have two boxes that are this much apart, the distance between them is the distance that you can't squeeze into, you can't walk into. So they stole some room. It's called excluded volume, right? So they stole some room from you. Okay, so but if you put them together, you gain that room, so you get less clutter. And this is sort of, these two ingredients together explain this collective behavior, this cooperative effect, is that once the swimmers see the particles randomly cluttered, effectively they feel like they are very cluttered themselves. So they come together. Once the cluttered particles are together, they gained all this extra room, and now they see like a very empty space, and then they can just swim away. This is sort of in hand-waving explanation what's going on, and then we wrote down the math for this, because it's just simple geometry of how much clutter space you're losing. and it just fell just on the experimental measurement. So we saw that there's a phase transition from this behavior to that behavior once you go past this cluttered concentration threshold. And there I realized that, okay, so now I'm doing something that is almost feels like intelligent, but once you add one more layer to it, you're really at the swarm level. What you see in, I think you will be in the swarm level, what you see in nature, and is to have an actual brain, like something that can compute, sense, have memory. And once you have something that is moving around, computes, sense, and has memory, you're just talking about a robot. That's it. And therefore, we got into this, what we do in our group, which is artificial swarm intelligence. So in Paris, I had the first project that sort of tried to marry these ideas together. Physical interactions. We had a fancy name for this, morphological computation. They do a computation with their shape. And more traditional learning algorithms. And there what we did was to put these two things together to do decentralized reinforcement learning on a swarm, on a physical swarm that uses both their interactions and their learning. So they can learn their environment, essentially. And we had a very simple question there. Can they learn how to find some target when none of them know where is the target and there's no gradient to lead them to the target, and they can just communicate locally with one another, but nothing external. So it's really decentralized. And we found conditions when would that work. But once you look at the math of it, it's very, very, very similar to the stochastic processes that you had for these individual molecules moving around and diffusing, for a cell that has to consume some nutrient, or for a lion that is looking for a zebra. It's very similar for the math. What we had there, which was kind of special, is that they had their internal space, their memory, which is what they learned, the process that they learned.
Because Dr. Benzayan, we are now we're in Paris. What year is it? And to what extent were these reinforcement learning capabilities of your like individual?
Very rudimentary, very simple, much less advanced. I mean, this was 2020 where we were doing this. So the project was slowed down a little by COVID, and there were some other things that, so even robots suffered from COVID. But it was very rudimentary, but for a reason. I mean, it was by design, because we wanted to be able to write analytically what we'd expect it to be. Their learning space was essentially, I mean, the way they were doing, it's called phototaxis, is they're trying to find the light, and you can have different types of phototaxis. So if you have a street light, if you turn around, the light is coming from that direction, so you can just go in that direction. But then there's a gradient, there's a direction, and we want to have no gradient, because there's nothing global that can lead you. And what we had was sort of like a spotlight. It comes from the top. So if you're in the light, you're in the light. If you're outside of the light, you are outside of the light, but you don't know, you can be right next to the light, but you don't know it.
Yeah, I see.
And the swarms, what we programmed into the swarm is that no one robot knows what's the actual target light source or light intensity that they're after. None of them knows. No explicitly, and if some of them do know, no one knows that they know it. Okay, so they somehow have to agree which robot has the correct algorithm.
So they had to communicate with each other.
Yes.
How did that work? Did they have Bluetooth or just Wi-Fi?
Yes. So it's IR. It's a little bit like Bluetooth. It's IR. We used like a hybrid approach. So in swarm robotics, many times what you do, you have commercial, like off the shelf robots. What I'm doing right now is actually to build our own, for a reason I'll explain in a second. But there are many real good robot platforms, swarm robotic platforms you can work with. Some called epochs, probably pogos. There are a few of them. This one was called kilobots. They're robots about this size, so 3 centimeters, and they have a light sensor, and they can communicate by they shine. They have it's like a remote control. Here, another prop, a remote control that shines to the floor, and then it sort of propagates sideways to the other robots, and then they can receive. So each robot has this transmitter and receiver, and then this is how they communicate. And they communicate in short range, so they can communicate with their, a couple of robot sizes away. And this is the short range is actually important here, because if they need to have all-to-all communication, it will not be scalable. If your algorithm relies on everyone communicating to everyone, it means that if you want to double the size of the swarm, you have to double their bandwidth, compute, and so on.
I see.
You need a different robot. So we're really working with local interactions here. And this is a very, physicsy way of approaching it. It's just local interactions, which is something that when you're doing classical ML, AI, you don't have to worry about. You say, oh, that neuron can connect to all the other neurons. All these layers are all connected to all, and so on, and it's fine, because there you can actually afford it. If you want to do something that is physical, it's harder to scale it up once you have not local interactions. So that was my postdoc in Paris, and then I found this. I started working here in the Donders. I'm looking towards, so it's roughly in that direction, in the Donders Institute for Cognition, in the Department of Artificial Intelligence. And what we do is, not just me, I do a very specific tack of it, is we call it machine learning and natural computation. Sometimes they call it neuromorphic computation, which is thinking, how do natural systems compute? How do they do intelligence? And it's very different than how we do it artificially. Right? Because artificially you have, say, it doesn't matter if it's an LLM or so on, you have a global cost function, which is very different than what you have in natural systems, that everything is local. Natural systems almost can't afford to have global information because they have to evolve, right? And if there's something global that tells them what to do, the individuals can't quite, who is in charge?
But you say everything is local, but you have, as a human, every cell has the same DNA, right? So is that not a form of a global
Agreed.
code?
Yes, you are right. There is some global, and they're all also measure the same temperature that is external. Yes, but the communication is not local, is not global.
Yeah,
it's not like every cell communicates with every other cell.
So every cell has the same source code a little bit, but then they are local.
Yes.
Yeah. And how they communicate. Super
And
interesting.
also, the cells themselves have some mutations in their DNA. So there is some width. There's some width to that distribution of that source code too. But yeah, can you have a system that has different DNA for different cells? Probably not, because you try to implant one patient's liver to another's or whatever, and then it doesn't work.
Incompatible. Yeah, they got to be compatible with it. But this is a really interesting way of thinking. I have another high level question for you. Is, as we look at nature and we see that things are localized there, the way like particles communicate with each other and form intelligence, do you think that's a missing piece in the puzzle to achieve actual intelligence? Because one thing that's clear to me, I love the current AI that helped me become a developer. Before that, I was just an idea guy, and now I'm making real apps and stuff. But I do know, and I feel it every day, that this is not what I would consider actually intelligent. Because it's very useful, but it's not intelligent. So is this maybe a missing piece of the puzzle?
So I have to say that the current development in AI, from a research philosophical point of view, I love it, because it forces us to ask this question: what is intelligence? What is actually intelligence? What does it mean? And to some extent, it feels very intelligent. You discuss, and it's amazing. I don't think there's a week that goes by and I'm like, wow, this is really amazing. This is changing. This is going to change tectonically a lot of the things that we're used to. Is it intelligent? To an extent, I don't know. Is my 5 years old who can do some of the multiplication table intelligent? Okay, maybe, I don't know. So yeah, it looks like it's a little bit intelligent. Is it the final bit, or is it? I think the local interactions is going to play a crucial role, for the following reason. And I think there's a researcher in Radboud. Her name is Fleur Rust. And she's working on computational neuroscience. I think that's her department. And she has a really nice TEDx talk about the difference between AI and like current AI and like our brains. And it's very quantitative, and I like it. So people consume something like 100 watts, give or take. So 3,000 kilocalories a day. You do the math, it's something like 100 watts. This is much my orders of magnitude less than a supercomputer consumes. Orders of magnitude, like so a supercomputer probably consumes in the megawatts. So 100 times less, or something like this, like something let's say 1,000,000 times less.
Yes, but
Now you need to run this 100 watts. You need like a peanut butter sandwich a day, practically, maybe a little more, but something like this. And now you want to have a self-driving car. Now, so you need to drive this computer that drives that car. You need a truckload of peanut butter sandwiches. Okay, but how are you going to drive that car then? It doesn't make sense.
Dr. Manzayan, I do have a counter argument directly from Sam Altman himself, because he said, people say like your brain runs on much less watts, but if you look at the evolution that we like how much energy was spent in the evolution that got us this brain, maybe it would be also a truckload of peanut butter sandwiches, right? Maybe that's a faulty argument of his, but then that's his fault. I'm just don't shoot the messenger. Don't shoot the messenger.
Well, we can do the math. We can do the math for this, right? We can estimate how many people existed, integrate over their lifespan. Yeah, we can do the math. But inference takes a lot of energy, not just the training. Even inference takes a lot of energy.
Yeah, even then we are more efficient.
Yes, much orders of magnitude much more efficient. So, and again, it tells you that, I mean, okay, so I don't think that the current LLMs are as intelligent as a person. There's clearly a difference. I don't know how to put the finger on it.
Because going back to your 5-year-old, might not be able to write a paper like an LLM would, but if you look at robotics, then your 5-year-old is much more capable than what we can do with robotics today. So there's clearly a missing piece, right?
And historically, when you see how robotics was developed, it was many times it came from the people who build robots are mechanical engineers, and people who program them are computer scientists. This is historically. Now it's the blur is there's so much a little more blurred to it. But it means that whenever you think about a robot as pixels, you forget that it's a physical entity.
Exactly.
Historically, it was much more useful to, I mean, the robots were just arms that were moving things in a factory. That was the robot. And now we want to make them autonomous and have them have agency and all these things. So we need a paradigm shift, because you can't have a whole, nuclear power plant inside the robot to drive its many peanut butter consuming CPU.
Hey, and I wanted to we're already a bit further down my plan, but I wanted to get back, because from our conversation, it's already in there, but I have a really clear understanding of how your background is useful to what you're doing today with the robotic swarms and the research that you're doing there with Radboud University. But I do want to ask you, can you explain to us one more time, why is it interesting? Is this because it's a missing puzzle piece? Why is this interesting to you personally, and why would this be interesting to the world?
So personally, I think it's interesting. It's a missing puzzle. It's a puzzle. You look at nature, you look at like swarms in nature, and swarm is a very like broad term that I use for describing collective behavior in intelligent beings. And it doesn't matter if it's, pedestrians that somehow walk past one another and make a coherent flow without anyone really telling them what to do. Or birds, if you see, I don't know if you got to see murmuration of birds, starlings. It's amazing. And it really is amazing. I mean, you look at it and you're like, what is going on? This is just mesmerizing. And we're nowhere near that technologically. We're nowhere near that. We can have a few drones, say, fly together in synchronicity in a decentralized way, but that's it. And that, like, nature does that in the tens of thousands very efficiently, and it's useful. This is how they evade predation. I mean, they can confuse a falcon that tries to attack them. It's useful for them. We don't know this. And from going back to my chemistry and material background, it looks to me like a material. It's like a fluid, just with not exactly Newton's laws of physics. It's something that we have to revise it a little bit. Probably Newton's at the bottom, but there's some other layer that once we capture it, we'll be able to reproduce it, because there are many models of how animals behave collectively. Very few synthetic or artificial examples of it. Very few. And even the examples that you show from our lab, it's so rudimentary compared to what you see in nature. It's humbling.
Let's grab those examples a bit and just talk about them a bit, because over here I have a picture or a figure where you can see do you see my screen, by the way?
Yeah.
Where you can see the little robots that are being used for the swarm. So they have some sort of a leg and they can vibrate, and by the vibration they move. Am I correct?
Yep.
Then I did my homework well. And then we had some videos prepared where they show some interesting behavior. I have here. Should I start with the simulation or with the actual video?
You can do either.
All right. So what are we looking at here?
So in the simulation, okay. So I have to narrate this because I don't know how well it shows on your screen. It's a bit jittery here.
I can do a little full screen thing.
Oh, now it's smoother. Oh, this is nice. Okay, so the little particles are simulated robots, and there are, I think, 1,000 of them in this example. And the bigger ring, the pink ring, is what we call the payload or a passive particle. And the little particles, they just run around. I mean, they don't have any target. They don't see, and occasionally they collide with one another, and also collide with the payload. And what we found in this paper is that under some circumstances, you can get them to spontaneously start pushing the payload cooperatively in the same direction. So alternatively, there are other videos from the paper. You can put them later on, or you can look at them right now. This doesn't necessarily have to be the case. They can also be just like symmetrically accumulating around the payload, or just colliding and flying off of it. And yet somehow they all align, choose a common direction, sort of agree on a common direction, and push. This is an experiment. The experiment, we can't have sort of periodic boundary conditions, so there's a finite size. But they push, and they usually push the payload to the end of the arena. And this is not always the case. And what we found is that there's a very simple physical condition, mechanical condition, that tells you when this is going to happen. And these robots, they don't have any sensors. This is like the simplest version that we can have.
We're not in Paris anymore. They have no reinforcement learning whatsoever.
Yes.
They're just vibrating around, and this happens.
We're not in Paris anymore, Toto. No. Yeah, because we realize that you can, even then, you can have something very complicated, or very sort of, I guess not trivial, just with mechanical interactions. And the mechanical interactions here is very simple. I mean, when they collide, they have, so if you if you push, how should I say this? Yeah, if you walk, you can try it yourself with a friend. If you walk and you have a friend come from the side and push you from the side, you'll find that you don't just get pushed sideways, you also turn. Okay? And this turning has to do with with your gait, with the way you're walking. And you can change the gait, or in the robots, you can change the mechanics of their legs, such that once you're being pushed, instead of being pushed away, you can turn into whatever is pushing you, which was a bit counterintuitive. This was sort of a accident that we found in the lab. We put a robot on a slope, and we let it run, and then we were expecting it to slide downwards, and it went up, and we were like, huh, this is funny. But now we have a mechanical understanding of this, but this directly translates to how they interact with the boundary or with an obstacle, because now an obstacle is applying the force, and the robot just turns to push against it.
Yes. But just to be clear again, this is a mechanical thing that you did to make it rotate that way, right? This is not programmed. This is just changing the legs a bit.
It's programmed into its mechanics, you could say. So it's like an analog computer in a way. It's like it's an analog response, but
Yeah.
there's nothing digital there or anything like that. Yeah.
And
And
you found,
so
you know,
for a long time, how do ants do it was not very clear, because ants. So there's one thing that they sort of figured out. There was a nice paper from Ofer Feinerman's group from Weizmann University, from Weizmann Institute. So like, how do ants know how to take the food that they forage to the nest? So they have their trails, but when a bunch of ants push or pull on something, how can they agree, okay, let's go to that trail? And they figured out what's going on, that there's one ant that goes through a trail, knows where it is, and then like tugs everyone. And this ant constantly shuffles, and everyone shuffles, so it's completely centralized. There's no one special ant. But it wasn't clear, how do they know how to push it in the same direction? Because like, how would they have to arrange themselves? And this gives you a very simple design. You just need essentially to play with their center of mass respect to where they're standing, and that's it. Now, I talked with Ofer about his paper, and he told me, ants also go up. And then he took an ant, put it on an inclined plane, it went up. And we're like, huh. So now we're trying to see if we may have an insight from robotics about animals, because many animals do it. Locust, all sorts of, even cellular algae does it. Some simple swimming mechanism, they tend to go up. So you just need to play with the mechanics, and you have an algorithm for this. So you've been in Edgar's defense. Edgar was a really good bachelor student in my group. Did a bachelor thesis.
I thought it was a PhD when I was sitting there.
No, it was wishful. It was wishful thinking. It was wishful. Like, it was a Freudian slip that I wish he would say for a PhD. Anyway, so he did a really nice job. And what he was doing was actually to take the robots picture and see how far you can push it back into the atoms analogy. Because there are some metrics and statistics and statistical mechanics that you use for atoms, and they're very useful in then designing materials. If you can show that, these, with the right adjustments, also apply to robots, then you can take all the knowledge, or a lot of the knowledge, this huge body of knowledge of how to design materials using thermodynamics, physical mechanics, and so on, and apply it to swarm engineering.
Yeah.
And that's what we're after.
And that is interesting, because now we get to the question of real-world appliances that Edgar, the student of yours, answered so brilliantly.
Really well.
Yeah.
So I always hesitant a bit when I get this question, because my pursuit is very scientific. It's very, very scientific. But what I do see is that swarm are an excellent amplifier of abilities. You can, so the thing is that if you look at industrial robots, their motion is many times predefined, and they have a hard time working together in cluttered environments. A very hard time. The Roomba that we all love and adore, it was developed by the way, one of the co-founders of the Roomba is Rodney Brooks. Maybe you heard that name. He talks about humanoids, and he says he's like very skeptical about humanoids, because he says a lot of our dexterity comes from the fact that we have like thousands of sensors all over our body, and this gives us the feedback. And this is not how robots are being built, at least not these days. So getting a humanoid, like an intelligent humanoid, is pretty far. and you've probably seen all these mock-ups of a robot that is, pouring a beer, but it was actually controlled remotely. And
Or the Kung Fu in China, the Kung Fu robots. Did you see them?
yeah. Trying to go away from violent examples, but yeah, the one that's pouring the beer, it looked very, I don't know, the actor did a good job until he got off his headset, and it's like you see the robot does this. They know that something is weird here. But it's in part because the physics, the mechanics was not introduced. So this is in a single robot level, but once you have many of them, they're in trouble because they're all moving. They're all trying to do something. And they need to somehow sync and coordinate implicitly.
But they will be, the way they're designed right now, they will be limited. But the teleoperator does show that if you have, like, the sensors are kind of enough to do a lot of things as well. Because if you can do it through a teleoperation, this person is also not feeling. They don't have all the senses that we have. They have only the vision and the audio experience in that room, and it still is able to do a lot of things and pour the beer. So in theory, we should be able, with like a Tesla Optimus robot or whatever, or the Figure One, to be at the level
To pour a beer.
To pour a beer. To pour a beer.
No, but this would be great. But now I want them to thread a string through a needle.
There they might be. That
So
might not
this
work.
is what we're talking about when we're talking about general intelligence. I mean, like, for one thing, they'll be good, maybe okay. Also the pouring the beer is, the pouring the beer is a bit. We're really helping these robots, and it's okay. They're at the beginning, right? We need to give them some slack.
But we're cheating.
If there was someone around them or something around them they did not expect, a human operator, a human, like, let's say, you turn around and you feel you're brushing into something, you stop.
Exactly. Yeah.
They wouldn't feel it. Even the human operator won't feel it, right? So let alone the robot. And this is where, you throw all the cups will fall off because someone left some cups over there. And this is where the robots still have a hard time, like, in unknown environments. And it's a big challenge. I mean, this is like, if you want to deploy a robot outside, how do you do it? How can they work together? It's hard. It's not an easy challenge. And I think in the coming decade, we're going to see many big steps in that direction. And anywhere from ocean exploration to underground exploration. So these are examples where you don't have necessarily global communication, so you can't communicate through satellite or have some drone that tells you where everything is. And space exploration also. Some planets are inhabited only by robots. Know that.
Yes, the Mars, right?
Mars, exactly.
Well, maybe there's Martians out there.
So they'll have to cooperate. They'll have to work together somehow.
I see. This is how I got interested in robotics, actually, because I was so intrigued by the idea of having a backup Earth, because I'm scared of climate change and stuff, and just humans doing stupid stuff. But then when you think through it, there's robotics is kind of the answer of how you solve it, because somebody needs to prepare that place. So now we're talking long timelines, I'm aware, but you would want to send some swarms of robots out there that might be even able to reproduce themselves and communicate with each other. Also localized. They cannot be connected to the cloud here. That would be slow. So yeah, that's very exciting.
So two interesting things for you to look into. You have some more homework. One, which one should I start with? Well, let's start with Neil deGrasse Tyson.
Yes, of course.
He has a very good argument for why planning our escape or our B plan on Mars is not a great idea, because colonizing Mars will be much, 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 much harder than solving our problems here. So we should probably solve our problems here. I understand you don't agree. You don't believe in the human nature, but it still might be better. And I think I agree with him. And this is coming from an astronomer, right? He wants to occupy Mars. It's like, the most fun thing for him to do. But he realizes this, like, this is the reason it might not be sensible, but it's very interesting to go there. Two, going back to Rodney Brooks. Rodney Brooks and Anita Flynn wrote a paper in 1987, I think. It's called Fast, Free, and Out of Control. It's a paper that was submitted to the U.S. NASA, I think, or I can't remember exactly. It wasn't a classic journal, and then it was turned into a movie where they argue that okay. The full title is "Fast, Free, and Out of Control." Uh, a robot approach for taking over the solar system, something like this. And the premise says that we need to start shaking off this idea of highly controlled robots. We need to agree that they're going to be fast, cheap, and out of control. Out of control means, it's a little bit like saying stochastic, right? There's noise. And this is how we can take over the solar system. But we have to revise how we think about robots. And this was already in 1987. So they really were visionaries of this idea. And this language came because they appreciated that the very controlled robot, sort of the classical robots that you had in factories that just move something from here to there in high precision, is not the way you want to engage with reality, which is noisy.
So I'm gonna do that homework 100%. This sounds so super interesting. And about the Neil deGrasse Tyson part, I totally am on your side with that. We should fix the issues here and achieve world peace would be awesome, for example. But what I do want to say is, like, if we really do a long time horizon and the sun will at some point implode, even if we fix all the issues here, Earth is temporary, so we need to escape the solar system one day.
The solar
And for-
system, not
Yeah,
just
even-
Mars.
I think we need to do like I saw like a little video about it from Kurzgesagt. We need to harness the sun as a certain sort of engine, so that we as humanity in thousands of years can keep on being human and being alive and having beautiful experiences. And for that we will need robots. But first, let's use nice robots to fix the problems here on Earth.
Two more references.
Okay, let's go.
I
Two
think-
more
I think you
references.
would love. I'm not just saying this. I think you love, and maybe also your audience. One is one is a reference, another one's a joke. So, do you know Isaac Asimov?
Yes.
He's a science fiction writer. I think he has a PhD in chemistry, by the way. He has a paper about a molecule that is extending into the future, and it can dissolve before you put water into it. It was like sort of something, but he has a nice short story. It's called The Final Question. Okay, and it's about essentially humanity asking, like, what are we going to do when all the stars die? Okay, and it's like it really leans, physics or chemical ideas and thermodynamics, but in a nice sci-fi idea, and it's super relevant for today, especially with the LLMs and the chatbots. The Final Question, Isaac Asimov.
I love it. I wanted to.
And the last thing is a joke that I just saw last week, and I think it was, I don't know, maybe it's a dad joke, but once the sun explode into, I think they say it's going to be a red giant, and it eats up, Mars, or sorry, what is it? Mercury, Venus, Earth, and I think also Mars, maybe also Jupiter. Then Pluto is going to tell us, so who's not a planet anymore?
Shots fired. I think I always have a feeling that Pluto is a planet, but I don't want to get the Plutonians in trouble. No, that's super good references, and I don't want to end this talk before I ask you two more questions.
Oh no. Yes, I'm listening.
We're talking about this decentralized swarm behavior as a missing piece to the puzzle to achieve like a low. deeper, like actually intelligent systems, and what that means is also still a question. But that's what we've been talking about. And let's, without going too deep in the definition of what it means, like we all have a sense for it. How long do you think until we will reach superintelligence? And do you think we will ever reach it?
So what is superintelligence? Well, let's start with that, because I don't know what it even means.
I think, okay. I was hoping you would just jump the fence, but I think it's a valid question. I think let's try to make a definition together right now. So super intelligence would be all the best humans in the world, what they can, the most expert humans in the world, like Einstein level genius humans, how we would describe them. They would be nothing compared to what this intelligence can do, and it doesn't have those weird blind spots that current LLMs have at all anymore. So right now, if you ask LLM, like, I got a funny glass and the top is sealed, the bottom is open, can I drink from it? The LLM says, no, you can't, it's impossible. Probably in the next batch of training data, they will figure it out. But those blind spots are not there anymore. This AI can do anything the best human has ever done and much more. So the best human in mathematics is dwarfed. The best human in music is so there won't also, yeah, it is really like next level in across domains. Is that a good enough definition?
Yeah. I think we will never reach it. I mean, something like that. But it's not, I don't think it's a human's problem or a machine problem. It's more of a mathematical problem. That example with the cup is really good. There was another example that was hyped a year and a half ago or a couple of years ago with the feathers. Do you see that?
No,
Friend, he asked all the chatbots, I don't know, OpenAI and Gemini and others, asked the following question: what weighs more, 2 kilograms of feathers or 1 kilogram of feathers? And all of them answered they're the same weight. And this is, of course, nonsense, but they were just trained on something.
On that joke. They were trained on that joke.
On this mental exercise with the lead, whatever, and feathers. And, he really tried to get them out of it. And they were so hard-coded on this, on what they were trained on. Like, at some point, he told them, okay, can you write this as an equation? It's like 2 kilograms of feathers equals 1 kilograms of feathers. And then he's like, okay, can you simplify this for me? And he's like, oh, yeah, here, I divide by kilograms of feathers on both sides, and you get 2 equals 1. And it says, wait a second, something is wrong. Oh, you cannot divide by kilograms of feathers. So it got to the wrong conclusion altogether. I think they fixed that following some, publicity of this thread. But it just shows you how sensitive they are to the training data. And the training data that you have in nature is so much more diverse and so much more complicated and so much more dilute than the repeated sort of jokes that we have and repeated examples that we have in the literature. And this is essentially how breakthroughs happen, right? So when you have new data, I mean, I'm very empiristic in nature. I want to see the data before I can start thinking about things. And if we don't have the data, how can we have a super intelligent oracle that you can ask it any question?
Yeah, it's a good question. Maybe you can't, right? But then we go.
I think like if it doesn't know what matters.
But then we go into human territory, right? Like Einstein was able, with the data that he had, to come up with new theories like E mc squared type beat. All right. Was that in his training data? Are we as humans capable of going beyond our training data? Because if Einstein was, then I think the right artificial system should be as well.
But Einstein didn't go beyond the training data. This is sort of the cool thing with the theory of relativity, and I mean, the data about the, so, okay, what does the E equals MC squared? This is why, having a PhD in physics is helpful, right? What's behind it? When you look at Maxwell's equations, you have to go really deep into it. When you look at the Maxwell's equations, so these are equations that tell you how electric and magnetic fields and electric charges interact with one another, right? So you move a magnet, you create an electric field. When you look at these equations and do some look at specific conditions of these equations, you get that an electromagnetic field travels at a constant speed, the speed of light. And now we interpret this and understand this is light. So an electromagnetic field travels at the speed of light. And from these equations, it seems like it doesn't matter who's looking at it. It doesn't matter if you and I are moving fast compared to one another or standing. If we believe these are the right equations that describe nature, this is how fast it should move, the speed of light, period. This was known since Maxwell, so 50 years before Einstein, and even before that, because Maxwell put everything together. But these rules came from experiments. It came from Faraday experiment, Faraday law, and Gauss law, and all sorts of experiments that that researchers conducted to see what nature does. And from these empirical evidence, they devised the equations from which there was this result that seemed a bit weird. It's like there's this constant speed. And it's weird because if you think about, for example, sound waves, if you move relative to the air, you can go faster than the sound wave. You'll have a different speed. You can go faster than the speed of sound. But with light, it's not the case. So this was sort of very counterintuitive, but the data was there. You needed to pause and appreciate that this is something very deep. Once you do that, then you get the connection to mass. You say, oh, actually, E equals MC squared. When the result was written in the paper also, this 1905 paper, also, it doesn't really talk about this. It talks about electromagnetism. And then it sort of comes out of as a result, but it came from data. It came from like repeated measurements that were at odds. So yeah, if we want this oracle that we can ask any question about, like, how fun is it to surf the red dot on Jupiter? It needs to know what's going on there. And this has to come from observations. Maybe we can teach it to observe. I don't know. Maybe we could.
So that would be also a missing puzzle piece here. We need intelligent systems that can go out and observe. That is another missing puzzle piece. So basically you're saying, I'm not sure if I believe that these types of, the way I just defined superintelligence will ever happen. But still, you're a positive person. I can feel it in the whole conversation, and you are so passionate about moving the needle with your work. So I have my last question for you, and then we can still talk a bit if you feel like you want to address some points. And my last question is, if we zoom out now and we look globally at the research community worldwide and the field of AI specifically, what developments are particularly interesting or exciting to you, and who should I invite next on this actually intelligent series?
You should have sent that question beforehand, so I would have been ready to suggest a few people.
But you suggested a lot during the conversation as well, so.
Yes, yeah. If you can get an interview with, if after me you're interviewing Rodney Brooks or Neil deGrasse Tyson, that'll be amazing. Or Isaac Asimov, he passed away, but I don't know. Maybe you can do it somehow.
Yeah, I could own him maybe.
Let me suggest. I can suggest a few people. Okay, someone that just comes up to my mind is someone from New York, Stefano Martignani. He does what is known as material discovery using AI. So, and I think he's a professor at New York University, professors of physics and chemistry, I think. So you're a bit stuck in this domain now that you started with me. But he really he uses AI to discover materials, to do material discovery, which is interesting because once you do experiments, experiments are hard. I mean, they take a long time, and you're dependent on all sorts of supply chains, and you need to evaporate something and clean it up. They take a lot of time. But if you can guide the design with something computational, it can be very useful. So I can send you his contact later. I think he might be a fun person to chat. You can talk with okay, so if we're talking about swarms, you can talk with Haiku Haman. He's a professor in Constance University. He wrote the book Swarm Robotics. So that's
his title.
yeah. When I read that book, I was actually when I read the first version, no, there's second edition. When I read the first edition, I was like at odd. I was like, actually, this is what I'm doing. I mean, the book is written more from control theory and more computer science the approach, and less sort of stochastic approach is the way I'm approaching it. But I realized this is basically what I'm doing, and I think he did the well-rounded job in compiling this book, because swarm robotics, because it involves like collective behavior and computer science and mechanics, and it's an amalgamation of a lot of topics. So writing a single book is very ambitious, and he did a good job. And now he has a second version, which is even better. I think if you can get a hold of him, it will be interesting.
Awesome.
I can give you another person but he's more of collective behavior. He's more doing
Behavioral sciences?
yes, collective, but in yeah. So there's Ian Cousin, I think. He's also from Constance, from the Max Planck Institute. If you get any of these guys, you're golden. So he does collective behavior in actual swarms, in natural swarms, in fish, and I think he's looking into bees also. Can't remember. Like, he does all sorts of things. So yeah, you're getting a lot of collective behavior stuff from me.
Yeah, but I think it's really interesting to dive deeper in this. You really excited me in this conversation. I think it is one of the missing pieces, and I think maybe these three people are already enough for me to dive into. Maybe we can do one last attempt into making this concrete for a builder like me and my audience. I hope that my Tag Amsterdam builder community is tuning in with us. Down the line of your research, a few more papers down the line, maybe one of us can start building applications with these swarm behaviors that we understand better thanks to you. What could that look like?
How can you use them?
Yes.
So one thing that I'm sort of toying with, an idea that I'm toying with, is using. This is specifically in drones, but it's very, 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 very preliminary. So if your builders are getting into this, they should expect a lot of pain. Is how can they do stuff together in delivery? Can they move things together? So if you have, if you want, say, a drone to pick up something, it has to be like, the drone has to be powerful enough, and usually big drones are very expensive. But if you have a bunch of smaller drones doing it together, the cost becomes much lower, the noise becomes lower, everything becomes better, but you need to find a way of getting them to work together.
And that should be localized then?
Yes,
if you want.
they somehow, there was actually a really nice paper, I think IEEE, I'll send it to you later, where they took a bunch of robots that held strings. Can't remember exactly the configuration, and they made a hitch around a bucket, and then they lifted it, and then they moved it around. I can't remember if it was decentralized though. I'm not sure, because I mean, many times when they're doing these experiments, at least at the beginning, there's some external camera that tells every robot where it is. So it's not really decentralized, but it might already be useful. It's because in a construction site, you want to pick up blocks,
Yeah.
and you can have just some camera here, and then a bunch of drones just moving the blocks around, and then all of a sudden you don't need a crane, you don't need a huge truck to move everything. You can come in small patches and make much less noise. So you can start opening
Yeah,
your head to these kind of ideas, but it's clear that they have to be able to interact physically. I mean,
Yeah.
if you're very sensitive to a collision, then you're in trouble. Then you're really much in trouble. So you have to think how they can work together.
This is an awesome direction. I hope. I see a lot of applications that could happen here. I hope it will be coming soon. I would love to work on something like that, actually, personally. And I want to recommend you and the viewers to look at. And I'm sure this is centralized though, but to look at the drone shows in China. They have like I was in Chongqing a month ago, and they had like a huge panda but it was formed of all these tiny drones. It was clearly not. It did not look organic. So if we look at your experiments, where there's kind of swarm-like behavior, this was clearly a grid of drones, Dr. Benzayan. So maybe this could also be like
these drones. These are a really good example of. I don't want to get too political about this, but about how these big shows of drones can be very catastrophic when they're done in a centralized regime or manner. And in these drone shows, which I mean, they're really amazing. They have, I think, over 10,000 drones. Each drone, they call it digital firework, right? So firework with no explosions. They have very high precision. It's a little bit like these arms that I was mentioning. They're very high precision.
Yeah, true.
And it's being, I mean, they're pre-programmed, and there is what is called an RTK. So there is an antenna that communicates to all of them and tells them exactly in a very high precision, I think millimeter or centimeter precision, where they are. And then they can, stay in that grid and create the picture, the three-dimensional picture that you want, and you can even have them all rotate together. Look up what happens when they collide. When one of them collides with another one, you have this domino effect that they all start colliding with everyone, and then you have just fireballs falling from the sky. And this happened a couple of months ago, I think, maybe a little more, in one of these shows. It's kind of scary.
That's scary. I didn't know that.
So I don't know if you were standing underneath that panda, but know that you were lucky. Because, I mean, this is scary. And in a way, it's because they're not optimized for such noise, for a collision. They're not, because this RTK is so reliable, you just assume that it's not going to happen. In nature, by the way, flying things do collide. Birds collide, bats collide.
And they know what to do. Like if they collide,
they have something. Yeah, they are structured to sustain it.
Yeah, and I'm also thinking further. If you for example want a swarm to do something, a drone swarm to do something much more far distance, it would be much better if they have a localized intelligence. Because for example, if you think of birds and you think of your use case, and we have something in Spain that somehow, because of the parameters, it's good to be shipped by drones. And we wanted to go all the way to the Netherlands. We could not have a drone swarm like that right now. That would not be the most optimal way. I think you would want to have, like, you can map out the trajectory, but you want on the way maybe to have a localized intelligence, so that they can
so they can correct. Yeah,
they can correct, they can avoid, and if somebody bumps into somebody else, the whole swarm kind of understands
adjust,
what to do. Adjust. Yeah.
You want to give them agency and autonomy to be able to respond to a changing environment. And the real world is very noisy, constantly changing, very messy.
Yeah.
So this is what we're working on.
And that's a brilliant note to end this on, I think. Great examples, great talk. Thank you so much for being here on the first episode, Dr. Benzayan. Yo, thank you for watching and listening, and follow me at Borvibe everywhere to stay tuned and be updated on when the next episode drops.